lecture 24 of our series on numerical methods in civil engineering, we will talk about analytical methods for parabolic and elliptic partial differential equations. We briefly did start talking about analytical methods for parabolic partial differential equations in our last lecture, and we said that we are going to talk about two solution methods. The first solution method will involve the use of eigenfunctions, which I said is a sort of generic method common to which can be used for all three canonical forms, and then we are going to use the method of Laplace transforms. So, we stopped midway, so I will just briefly go over the parts that we have already covered. So, we are considering the one dimensional heat flow through a ring of circumference 1, and we saw that in that case we have periodic boundary conditions, and the periodic boundary conditions are on the primary variable temperature and its derivative with respect to space. So, if you assume solutions of the form t is equal to e to the power nx, where enx is nothing but the eigenfunctions, and e to the power minus lambda n k by kt is the time dependent part, right. If we assume solutions like that and we substitute it in my original differential equation, in my original diffusion equation, then I get the eigenvalue problem. Left hand side I have a linear operator, right, and the right hand side I have this eigenvalue, and this is my eigenvector, right. And I solve the eigenvalue problem subject to homogeneous boundary conditions. So, in this case the periodic boundary conditions. Again, so this is my problem, this is my eigenvalue problem. So, how do I solve the eigenvalue problem? I solve the eigenvalue problem assuming that Enx has a certain form, and that allows me to convert the differential equation into an algebraic equation. I solve that the algebraic equation, that is a characteristic equation. The root of those characteristic equations are my eigenvalues. I solve for the eigenvalues, and once I solve for the eigenvalues, I get my eigenfunctions. I know my eigenfunctions up to certain undetermined constants, right. I know my eigenfunctions up to certain undetermined constants, and I evaluate those constants by imposing my boundary conditions. So, in this case the boundary conditions are these ones, right, which we already talked about, right, and then on imposing those boundary conditions on these two, I get two equations, two unknowns, and you can see this is a homogeneous equation. So, for this system of homogeneous equations to have a solution, the determinant must vanish. Determinant vanishes, gives me this condition cos of omega equal to 1, which tells me omega equal to 2n pi, n is equal to 0 plus minus 1 up to infinity, right. So, now I know my entire eigenfunction. I know not only I know the constants also, right. So, I know my constants. So, now I can write my solution in terms of the eigenfunctions, right, and some coefficients, which coefficients are functions of time, right, and then I substitute. So, this is my Fourier expansion, right, this is my Fourier expansion. I substitute this Fourier expansion in the governing equation. So, now I get a function, a first order differential equation in time, right, in time. So, that gives me the undetermined constants tau n, which are functions of t. So, this is a ODE for tau n, and then I solve this ODE for tau n using my initial conditions, right. Subject to initial conditions, I solve for this, I get my tau n, right. I first, before doing that, I have to represent the initial condition in terms of the eigenfunctions, but that is just an intermediate step. But once I do that, I finally solve for tau n and I get this, and once I get tau n, I have the whole Fourier expansion for my temperature, right. However, one important thing to observe is that the time dependent coefficients in the Fouriers, unlike the time dependent coefficients of the Fourier solution for the wave equation, for the diffusion equation, the time dependent coefficients decay exponentially, right. You see this term minus k 2 pi n square t, right. So, it means that as time increases, this becomes smaller and smaller, right. Another but for the wave equation, if you go back to the notes to the previous lectures on the eigenvalue solution for the wave equation, you will find that in that case the time dependent part was not one exponentially decaying, it was not an exponential function at all, it was a harmonic function, so it was of an oscillatory nature, right. Here you can see it is very different, it decays with time, as time increases it goes down, right. So that is because of the fundamental nature of the problem. We are modeling heat diffusion, and heat diffusion inherently it's decaying in time, right. It's because of its decaying nature. As if you think of something like this, you have a boundary, right. You have a body, you apply heat boundary temperature boundary conditions, right. Then over time you would expect all those peaks initially, since you are applying the temperature at a boundary, you would expect the temperature to be high at a boundary, right. And then in the interior the temperatures would be smaller at starting with, right. But over time they are going to decay, those peaks are going to decay, and you are going to reach some sort of steady state condition, right. So that is exactly what we are trying, what the solution is telling us here, right. The solution is telling us that the time dependent part of the solution is going to decay with time. So the solution is going to be eventually, it's going to, the steady state solution is only going to have spatial dependence, it is not going to vary with time. So once it reaches steady state, things don't change with time, right. It's the equilibrium solution, you can think of it like that, right. Things don't change with time, they may vary over space, but they don't change with time anymore, right. So that is what the solution is telling me. The solution of the heat equation also has an oscillatory part, but that is purely spatial, right. The time part does not have any oscillatory part. You can see I, e to the power I, let us go back and take a look again. The time dependent part has no imaginary number, right. So it does not have any oscillatory part, does not have any harmonic components. However, the spatial part has an I, right, the e to the power minus 2n pi 2 pi I n x, right. So there is an so that is an oscillatory part, right. Using de Moivre's theorem, you can write it in terms of cosines and sines, right. So that has an oscillatory part, but the time dependent part has got no oscillatory contribution at all. So that is going to decay if you run it, if you look at it after sufficiently long times. So it has an oscillatory part that is captured by trigonometric spatial dependence of the eigenfunctions E and x, but what is important is that the higher oscillatory modes, right, even in the space there are oscillatory modes, and those oscillatory modes will have different frequencies. Some will have low frequencies, some will have high frequencies, and from the expression for those modes you can see that as n increases, the frequency is also going to increase, right. For larger n's, those oscillations are going to have higher frequencies, while the smaller n's, they are going to have lower frequencies, right. So, but you can also see that those higher oscillatory modes are going to decay faster. Why? Because n also appears in the coefficient of the time dependent part, right. So as n increases, this thing is going to control the decay. So the higher modes are going to decay faster, right. Higher spatial modes are going to decay faster in time, right. So when actually t goes to infinity, we can see that if we look at this expression, right, tau n t is equal to sigma n equal to minus infinity to infinity, right. You can see when t goes to infinity, the only term that is going to survive is for n is equal to 0, right. All the other terms are going to give me 0, are going to go to 0, right, while for n is equal to 0, this term is going to go to 1, right. So only the term involving n equal to 0 is going to survive, and because of that, in the limit when t goes to infinity, t x t is equal to tau 0 0, right, and which tau 0 0 we know from our eigen expansion of the initial conditions, from my eigen expansion of the initial conditions. Let us go and take a look at that again. So, tau 0 0 is equal to E 0 x T x 0. E 0 x comes out to be 1. So, it is basically the integral from 0 to 1 of T x 0 dx, right. So, that is going to be this. So, the final temperature at infinite time, at a very long time after I apply my initial conditions, is telling me that it is nothing but an average of the initial temperature. It is an average of that initial temperature distribution over my domain of interest, right. So, that's for the periodic problem with periodic boundary conditions. We can use the eigenfunction approach for non-periodic boundary conditions as well. I am not going to solve that problem because we have already done enough with eigenfunctions, but you can be verified that the solution of the following 1D heat conduction problem in a bar with homogeneous boundary conditions. So, now you can see the boundary conditions are no longer periodic, they are homogeneous, right. So, T at 0 is equal to T at L is equal to 0, right. So, they are both 0 at the two ends, right. The temperature at the two ends is fixed and it is at 0 for all times, right, and I have an initial condition which is T x 0 is equal to T 0 of x. So, if I solve that using the method of eigenfunctions, I am going to get a solution like this. Again, you can see that even in this case, even for the case of non-periodic boundary conditions, the time dependent part decays exponentially, right. The time dependent part decays exponentially, while the spatial part has a harmonic nature, right. The spatial part of the solution has a harmonic nature. So, the fact that it is decaying exponentially, the time decaying part is time dependent part is decaying exponentially, has got nothing to do with the boundary conditions. It has got absolutely everything to do with the fundamental nature of the diffusion problem, right, of the diffusion problem, right. When as time goes, right, it tries to reach a steady state, and steady state means that all those transients, all those initial conditions, right, with they decay, right. So, decay and things reach some sort of an average equilibrated state. So, next we will solve the same problem, but with boundary conditions, non-homogeneous boundary. So, I am going to solve the same problem, right. I am going to solve the same problem, but now I am going to assume that I have non-homogeneous boundary conditions, and I am going to solve that using Laplace transforms, right. I am going to solve that using Laplace transforms, and the homogeneous non-homogeneous boundary conditions that I am going to assume is that at the end x is equal to 0, I have a functional dependence on time. I know a known function of time, the temperature is a known function of time. At the end L, I know the temperature as another known function of time given by g of t, right. And we will solve this problem by dividing it into 3 separate problems, right, and we will use the principle of linearity, right, linear superposition, right. So, the solution of the original problem can be obtained by superposing 3 problems. So, one problem I am going to have initial conditions. The first one, del T1 del T is equal to k del 2 T1 del x square. So, that in that one I am going to have homogeneous boundary conditions, but I will have non-homogeneous initial conditions, right. You can see this T1 x 0 is equal to h of x is my non-homogeneous initial condition, and then I have homogeneous boundary conditions which tell me that at end 0 and at end L the temperature is always 0 at all times, right. So, that is the first one. Then I have another one, del T2 del T is equal to kappa del 2 squared T2 del x square, and in this case I have homogeneous initial conditions, but I have homogeneous and I have homogeneous boundary conditions at one end, but I have non-homogeneous boundary conditions at the other end. So, in this case I have homogeneous boundary condition at the end L, but I have non-homogeneous boundary condition at the end 0, and the third one is just the sort of the conjugate of that. So, in this case I have homogeneous boundary conditions at end 0, but I have non-homogeneous boundary conditions at end L, and both 2 and 3 have homogeneous initial conditions. So, if I superpose the solution of these three, I am going to get the solution of my original problem. I am going to get the solution of my original problem, and you can see if I add all those boundary conditions and initial conditions together, they are exactly the boundary conditions and initial conditions of my original problem, right. Now, the first problem I am not going to solve, because I have already solved this one, right. I have already solved this, right. So, I know the solution. The second problem and third problem are near identical, right. So, if I can solve problem 2, I can solve problem 3, because they are just the mirror image of each of the other, right. So, if I can solve problem 2, I can solve problem 3. So, I am going to focus on the solution of problem 2, right. So, we will therefore concentrate on problem 2, right, and we can rewrite problem 2. In order to do that, we are going to rewrite it to simplify it somewhat for the solution purposes. So, I am going to rewrite this I am going to get rid of the 2, right, because now I am only interested in problem 2. So, there is no need in keeping that 2, that subscript 2, carrying that around. So, I am going to remove that subscript 2, and I am going to replace kappa by 1 by gamma square, right. I am going to replace kappa by 1 by gamma square, and then I have these boundary conditions and initial conditions. So, T homogeneous initial conditions, non-homogeneous boundary condition at end 0, homogeneous boundary condition at end L, and I am going to solve that problem. So, before doing that, let us go back and recall what is the Laplace transform. So, Laplace transform of a function t, right, which is a function of x and t. If I do Laplace transform in the time domain, I get something like this: t tilde x s is equal to integral from 0 to infinity e to the power minus s t t x t dt. So, you can see here the variable of integration is t. So, after integration t vanishes, and you have a function in S, right. You have a function in S, and x, nothing is changing, right. X just goes along for the ride, because we are not integrating with respect to x at all, right. So, that is the definition of the Laplace transform, in case you do not remember. So, also we have expressions for the derivative in terms of Laplace. So, if I have d2, if I have the second derivative of function with respect to time, or I have the first derivative of function with respect to time, or for that matter if I have the nth derivative of a function with respect to time, I can do the Laplace transform of those derivatives, right. And there is a simple rule, right, which tells me how I can find the Laplace transform of the nth derivative of a function, right. So, if I have t to the tn, which means dn dtn of t, right, of the function t, then if I do the Laplace transform of that, I can write that in terms of the Laplace transform of my original function t tilde x s plus the initial conditions, right. So, the derivative, the Laplace transform of the derivative of t, the nth derivative of t, can be written in terms as a polynomial in S, and it also involves the Laplace transform of my original function, which is t tilde x s, and these quantities t x 0, t 1 x 0, t n minus 1 x 0, and so on, right. So, my derivatives, right, it involves my derivatives, and those derivatives are evaluated at time t is equal to 0. So, they all involve the initial conditions, right. So, they involve the initial conditions. Therefore, since we are if we are interested in finding the Laplace transform of the first derivative, then n becomes 1, right. So, in that case I get t tilde 1 x of s, that is the Laplace transform of d t d t, right, d capital T with respect to small t, derivative of capital T with respect to small t. If I want to find the Laplace transform of that, then I get s to the power 1, right, s to the power 1 t tilde x s, which is nothing but the Laplace transform of t itself given by that expression, and the value of that function at the initial time at t x is equal to 0, right. So, this is my Laplace transform of the first derivative of t capital T with respect to time, right. And therefore, if we use this in that equation, if I use that in that equation, so the left hand side involves the first derivative of t with respect to time. So, I know how that is going to transform as, so that is going to transform as this, right. And so, if I substitute that, I get an equation like this, right, equation like this. So, the dependence with respect to x remains just the same, right, because there is no transformation in the spatial domain up till now at least, right. So, nothing changes, right, and then I have the transforms of my boundary conditions. I have the transforms of my boundary conditions, right. So, what were my boundary conditions? My boundary condition was t 0 t is equal to f of t and t L t is equal to 0, right. So, these were my boundary conditions. So, I do the Laplace transform of the boundary condition and I represent the Laplace transform of f of t as f tilde s, and in this case of course it is 0. So, nothing changes, right. You can see that Laplace transform of 0 is not going to give you anything, right, that is still going to be 0, just from this expression you can see. Okay. So, this is now my transformed problem. This is now my transformed problem, and you can see that this is a second order ordinary differential equation in. So, it is now no longer a partial differential equation, it is an ordinary differential equation in the spatial variable x, right, because we have got rid of all those derivatives with respect to time, right. When we do the Laplace transform, we remove those derivatives and replace them by these algebraic expressions, right. So, we have got rid of the derivatives with respect to time, but since we have taken transform only in the time domain. So, those derivatives with respect to x remain, and I get an ordinary differential equation in x, a second order ordinary differential equation in x subject to two boundary conditions at 0 and L. If I want, I can integrate that twice and find my t tilde in terms of x, right. I can do that, and then if I want, I can do an inverse Laplace transform and get back my time dependence, right. So, that is one way of doing it. So, it is an ODE in x which can be integrated to obtain t tilde, then I can do an inverse Laplace transform to get my final solution t. However, here we are going to pursue an alternative approach which will involve doing an additional Laplace transform, this time in the spatial domain, this time with respect to x, right. So, that is just identical to that previous expression that we saw, right, which is the Laplace transform in the time domain. So, Laplace transform in the spatial domain is very similar, right. So, it is very similar, except now the integration is performed with respect to the spatial variable x instead of time, right, and once you perform the integration, the x goes away. So, you have p left and you have s left, which was the which resulted from the Laplace transform in the time domain, right. So, again we use the result on the derivatives, right, because we have now in this expression we have a second derivative in terms of x, right. So, if we want to find the Laplace transform of that second derivative, we again use this expression, right, but now we are going to our variable of interest is x, right, not t, right. So, if we use exactly that same expression for the Laplace transform of the derivative, we can see that the Laplace transform of the second derivative with respect to x, right. If I do that using that expression, I get something like this, right, something like this: p square t tilde p s minus p t tilde 0 s minus t tilde 1 0 s, right. So, this t tilde 1 is now the derivative with respect to space, right, it is with respect to space, right, it is with respect to x, right. So, and again we replace t tilde 0 s by the transform of f of x, right, we already got that before, right. T tilde 0 s is equal to f of s, f tilde of s, we already got that, right. So, we do that and then we get Laplace transform of del 2 del x square t tilde x s to be this: p square t tilde p s minus p t tilde 0 s we have just replaced by that, by the transform of the boundary condition, minus t tilde 1 0 s. This is something which we do not know, right, because in my neither did it appear in my boundary conditions, right. My boundary condition didn't tell me anything about the first derivative, right. It just told me about the function value at 0 and L, right, didn't tell me anything about the first derivative. So, I do not know that value, right. So, derivative it is the derivative with respect to x of the Laplace transform of t x t in the time domain evaluated at x is equal to 0. So, I do not know anything about that. For the time being, we will treat it as an unknown, right. Let us carry it along and treat it as an unknown, right. And then using this expression and substituting it in my equation here, using that expression in my equation here, I get the following equation. S t tilde is equal to p square pi gamma square t tilde minus p by gamma square f tilde s minus this, right. This I already know, and t tilde ls is equal to 0. So, now again this is a totally algebraic equation, right. So, I have got rid of all my derivatives. I have got rid of my derivatives with respect to space, I have got rid of my derivatives with respect to time. So, this is a purely algebraic equation and I solve for t tilde ps in the transform domain, right, in the transform time and spatial domain. I can solve for t tilde and get an expression for t tilde, right. However, I still do not know this quantity. So, we can first, so once I know t tilde, then I have to do the inverse transform, right. I have to do the inverse transform. In this case, I have to do two inverse transforms, right, with respect to space as well as with respect to time, right. So, in this case, I do the inverse transform with respect to space first, right, and I get back an expression t tilde x of s, right, my p vanishes and I get back t tilde x of s, which comes out to be this, right. I have not talked too much about how to do the inverse transforms, that is going to take too long, but you can look up in any good book on engineering mathematics on the inverse Laplace transform. It is very similar to. So, this is the after doing the you can find the inverse transform. So, on this after doing the inverse transform in the spatial domain, I get this, and on this I impose the condition that t tilde ls is equal to 0, right, this condition I impose that condition. So, then that using that I find out this value t tilde 1 0 s, I find out that value and that value comes out to be something like this. So, now I know my t tilde x s totally, right. I know this value also, which I have evaluated by imposing that transform of the boundary condition of the spatial boundary condition at end L, and so now I know my t tilde entirely. So, all I need to find my t is to do a reverse transform, is to do an inverse transform to get back my time dependence, right. to get back my time dependence, and if I do that, I finally get t tilde xs is equal to something like this. Oh, substituting, sorry, this is not, I haven't yet performed the transform. I just substituted that. Oh, I am just saying that I have substituted that here, right. I have substituted that here. So, I get my expression for t tilde xs, and that comes out as this. So, and I do the inverse transform in the time domain to get t of x of t, right, t as a function of x and t. I have not talked about details of the inverse Laplace transform. Here is a very good reference where you can find all you need to know about it, right. Okay, so we briefly talked about the fact that the solution to the diffusion equation has a time dependent part which is decaying exponentially with time, right. So, if we look at the solution after sufficiently long time has elapsed, right, then we can expect the temperature of the bar to reach an equilibrium, right, an equilibrium solution, and that equilibrium solution is known as the steady state solution, right. That is the steady state solution, and basically the steady state solution says that the solution is no longer varying with time, right. So, what does that mean? That means the partial derivative of T, my temperature, with respect to time, in the limit t goes small t, meaning time goes to infinity, must be equal to 0, right. And in that case, my parabolic equation becomes an elliptic equation. Why is that? Because the left hand side becomes 0. Let us go back and look at my original equation. Unfortunately, I do not have that. I must have it somewhere. For instance, let us look at this, right. So, when this thing goes to 0, so I have only this, the left hand side left, right, and that is like the Laplacian, right, Laplacian in one variable in this case, but that is like Laplacian. So, it is the elliptic equation. It is the third canonical form which we haven't yet talked about in any great detail, right. So, that is the elliptic equation, Laplace's equation. So, in this case the equilibrium equation becomes this, right. So, again this equation I can solve subject to the boundary conditions. So, I do not need any more initial conditions, right, because my I am looking at a solution after a long time, right. So, whatever effect the initial conditions had have now totally died away, right. So, now I can solve that problem. So, that is oftentimes, like for instance, for the parabolic equation, if somebody is not interested in the transients, it often happens, right. If we are not interested in the transient solution, right, we are just interested in the steady state solution of a problem, right. We do not care how the temperatures are varying when just after I have applied the initial conditions. I am just interested in the temperature distribution of my domain after everything has reached steady state, right. So, in that case I do not even solve my transient problem. I do not solve my parabolic equation. I straight away throw away my left hand side, I throw away my time dependent solution, time dependent part, right. So, make that derivative with respect to time equal to 0 and solve Laplace's equation after subjecting it to those boundary conditions, right. So, that is the solution of the steady state problem, right. So, the limit equation where all time dependent effects have died away is an instance of Laplace's equation in 1D, an instance of the canonical elliptic equation. In multiple dimensions, for instance in 3D space, the limiting form of the heat diffusion equation is nothing but Laplace's equation in 3D, right, which is given by that. So, there are many other instances. So, this is one instance where we saw that the parabolic equation becomes the elliptic equation after, if you look at it at a sufficiently long time after I specified my initial conditions. But there are other situations where the Laplace's equation arises naturally from the physical nature of the problem, from the mechanics of the model, right, from the physics of the model, right. So an interesting case involves the mechanics of a soap film or a bubble. You can think of a bubble. When somebody blows a bubble, there is a ring, and somebody blows a soap bubble, right. So that thing expands, right, and so the mechanics of that, right, is governed by Laplace's equation. And actually this analogous problem is used in a number of places, right. Basically it's a problem of a membrane, right. The soap film or the bubble, right, it's basically a membrane problem. There is a very thin membrane subject to some edge conditions, and then I am applying transverse loads, right. So here is my ring, here is my little ring, right, here is my little ring, and then initially everything was flat, right. I have a really thin film, right, connected to the edges of the ring, and then I applied a transverse load, so the little thin film bulges out, right, which is represented by this blue line out here, right. So this blue line here, this blue dotted line represents the deformed shape of my soap bubble, right. But the solution of this problem is useful in a number of places, right. It can be used to find the solution. It can be used to find this, to solve the torsional problem, right. For thin walled sections, if you remember, there is something called the Prandtl-Royce equations, right, and those equations can be solved using this analogous, this soap bubble or thin film analogy, right. So if we can solve that problem, it can be solved, the solution can be used in a number of situations, right. So for instance, the torsional stress distribution in thin walled sections. So how do we solve that problem? Well, we denote the displacement of the membrane from its unstressed position as u, right, and then we can show from force equilibrium. I haven't gone into that, but if you look at any advanced strength of materials book, you will find how they got that equation, right. So the equation, from force equilibrium, we can show that the displacement of my soap film or of my membrane must satisfy this condition, which is nothing but the Laplacian in 2D, right. It is nothing but the Laplacian in 2D, and which is equal to 0. So Laplace's equation in 2D, right. So now we need to solve Laplace's equation subject to the ring boundary conditions, which we can do like we parameterize the ring by the arc length along the ring, right, and then we prescribe the displacement along the arc length, right. U is equal to u0 of s, and we solve that problem, right. So that soap film problem can be solved using, that is nothing but the solution is nothing but the solution of Laplace's equation subject to the appropriate boundary conditions. Another problem which arises in civil engineering applications is of potential flow, right. So suppose we consider the flow of an incompressible fluid, right, for instance water. People in hydraulics interested in fluid, with how water flows, right, and solving the equations of motion, right. So we are here the problem becomes complicated because it is a constrained problem. And what is the constraint? The constraint is that the divergence of the fluid velocity is here. The primary variable is the velocity of the fluid, right, and the fluid is, if it's something like water, it is incompressible, right. That fluid is not compressible at all, right. Water has a very huge bulk modulus, right. So you cannot compress water at all, right. So than that condition we can show, I mean, some complicated mechanics, not really complicated, but some basic continuum mechanics, one can show that incompressibility constraint can be enforced by imposing this condition on the velocity of the fluid, right. And what is that condition? The condition is that the divergence of the velocity must be equal to 0, right. Now, in addition, if I assume that the flow is, suppose I am considering flow through a pipe, and suppose I assume that there is not much friction, right, there is not much friction, then I can also assume that the flow is irrotational, right. The flow is irrotational, and what does that mean? That means that the curl of the velocity is equal to 0, right. This is the curl, right. It is also, it is like it's the cross product of the gradient operator with the velocity, right. So, the curl of that flow is also irrotational. The flow is irrotational, which means that the curl of the velocity must be equal to 0. And if the curl of a vector, the velocity is a vector, if the curl of a vector is 0, then we know that that vector can be obtained by the gradient of a scalar, right, of a scalar function, right. So, that is, it can be shown that if the curl of a vector is 0, then the vector field can be obtained as the gradient of a scalar potential, right. In that case, I can get my velocities. There is, what I am trying to say is that there is a potential, there is a scalar potential whose gradient if I take, I am going to get the velocities, right. I am going to get the velocities. So, u is equal to grad of phi, where phi is a scalar potential. Then the satisfaction of the incompressibility condition. What is the incompressibility condition? It is divergence of u must be equal to 0. U, I am saying that since u is irrotational, u has to be equal to the gradient of a potential. There is you can always be obtained as the gradient of a potential, right. So, what does that mean? Divergence of u, that means divergence of the gradient of a potential, and I am denoting the potential as phi. So, divergence of gradient of phi got to be equal to 0. So, that is what my incompressibility constraint translates to, and divergence of gradient is nothing but the Laplacian, right. So, divergence of gradient is nothing but the Laplacian. So, what it tells me is the Laplacian of phi, where phi is my potential, is my scalar potential, got to be equal to 0. So, instead of solving directly for the velocities in this case, if I can solve this equation for the potential, I can get my velocity just by taking the gradient of that potential. So, that is why it is called potential flow, because ultimately I am solving for the potential phi, right. So, again we solve this subject to boundary conditions, right. Laplacian of phi equal to 0, we solve that subject to boundary conditions, and typical boundary conditions arise, for instance, when you have fluid flow past a solid body, right. There is a solid body sitting there, and suppose some sort of a rock, right, sitting there and there is the fluid flowing past that stationary rock, right, fluid flowing past that stationary rock. So, in that case, what are my boundary conditions? The boundary condition is just that n dotted with u is equal to 0 for all x belonging to B, I am sorry, this should be x belonging to del B, right. Del B is the boundary of the fluid, and as n is the outward normal on del B. So, I have this little rock sitting there, and I have fluid flowing past that rock, and I denote the surface of that rock as del B, right. And on that rock, once the fluid velocity has got to be 0, right, because there is no fluid penetrating that rock, right. So, once at the boundary, at the interface, n dotted with u is equal to 0, right. So, the normal velocity of the fluid is 0 at the interface. So, this is my boundary condition. This is a typical boundary condition. There can be all manner of boundary conditions, but this is a typical boundary condition, right. So, you have that, right. So, what this tells me is that my fluid cannot penetrate the rock, but the fluid can flow past the rock, right. So, the tangential velocity of is not 0, but the normal component of the velocity is 0, right. and we are going to look at two main types of boundary conditions for the Laplace for the elliptic equation, for Laplace's equation, and they are known as I might have mentioned them earlier in the course of this lecture, but here we are going to talk about them in slightly more detail, the Dirichlet and the Neumann boundary condition. In the Dirichlet boundary condition, we specify that the boundary condition is specified directly in terms of the primary variable. In this case, our primary variable is phi, so it is prescribed in terms of phi is phi. So, phi is equal to some constant on some boundary, right. So, as somebody tells me solve Laplace's equation, given that I tell you that phi has this value on the certain part of the boundary, right. So, that is a Dirichlet problem. The Neumann problem, I solve Laplace's equation subject to the condition that somebody tells me, well, I don't know what the actual value of the primary variable is on the boundary, but I can tell you what the derivative is, right. In this case, if somebody tells me, since I am looking at this little problem of fluid flow past a rock, somebody tells me that I know the normal derivative of phi, right. I know del phi del n, and it is equal to 0 on the boundary, right. If somebody tells me that, that is a Neumann problem, right. Both are well posed, right. Both are well posed problems, and I can solve them. I can solve both of them. So, if I consider the solution of Laplace's equation of volume B V subject to Neumann boundary conditions, we can see that if we integrate Laplace's equation over the volume, what do I get? So, this is my equation, which must be satisfied at each point, right, at each point in the domain, in each point in the volume B V, but suppose I integrate over the volume V, right. So, again this equation has got to be true, because Laplacian of phi is 0 pointwise, right. So, if I integrate that over my volume V, that had also better be equal to 0, right. So, in Laplacian of phi, I know that is equal to the divergence of the gradient of phi, right, and then I use my divergence theorem. I use my divergence theorem to convert that volume integral to a surface integral, right. I use the divergence theorem to convert that volume integral into a surface integral, which involves the normal, the surface normal, and the gradient of phi at the surface, right. So, it is the dot product of n with the gradient of phi, and this is nothing but the directional derivative of phi in the direction n, right. So, it is del phi del n ds, right. But suppose I am solving Laplace's equation subject to Neumann boundary conditions, right. And what do my Neumann boundary conditions tell me? They tell me that I know what del phi del n is at the boundary, right. Suppose somebody has told me that del phi del n is equal to d at the boundary, but then if I substitute del phi del n here, if I look at del phi del n here, you see that del phi del n is appearing on the right hand side, and it is appearing within an integral over my boundary. So, this condition imposes an additional restriction on the Neumann boundary condition. What it tells me that you cannot specify the Neumann boundary condition for Laplace's equation in any arbitrary way you like, right. The way you the boundary condition you specify, right, the del phi del n value you specify must be such that if I integrate that over the boundary, I get 0, right. So, you cannot specify any arbitrary dependence on the boundary, right. So, del phi del n can be a function of s, right, because this is an integral over s. So, del phi del n can vary over the boundary, right. You can specify that your normal grade, your derivative of phi in the normal direction is varying across the boundary, but it cannot verify in any arbitrary fashion, right. It must satisfy the condition that if I integrate that derivative over the boundary, it's got to be equal to 0, right. So, that is very important, right. So, because Laplace's equation itself imposes this additional constraint on the Neumann boundary condition, right. The Neumann boundary condition must be such that the integral of del phi del n over the boundary must be equal to 0, or integral of del phi del n del v is equal to 0, right. Now, a function phi of x which satisfies Laplace's equation is said to be a harmonic function, and harmonic functions are very useful because they possess certain very characteristic and important and useful properties, right. And one of those properties is that they satisfy what is known as the mean value theorem. What is the mean value theorem? The mean value theorem tells me that if I have a harmonic function, then I can find the value of that harmonic function at any point x0, right, x0, if I integrate that harmonic function over a sphere of any arbitrary radius, centered around x0, right. So, I want to, this is very important and it is very, very powerful, right, because what it is telling me is that I want to find the value of that function at a point, right. To find the value of that function at that point, all I need to do is to integrate. If I have the function specified on a boundary, right, I need to integrate that over the boundary, and that boundary need not be at, it can be any sphere, right. So, over any sphere with center x0 in the domain of harmonicity. So, find the value of phi at any point x0, all I need to do is to integrate phi over a sphere with center at x0, right, and that sphere can have any radius. So, I integrate that function over that sphere, that is going to give me the solution over. I have to normalize, of course, this is the mean value, right, and then I divide it by my area of the sphere, by surface area of the sphere. So, integrate it over the sphere divided by the surface area of the sphere, I get the value of the function at the center of the sphere. So, we are going to show why the mean value theorem works next class, and we are going to show that in spherical coordinates, right. I will just introduce spherical coordinates and then end this lecture. So, spherical coordinates, well, that is just a coordinate system which says that if you have any point, right. So, the spherical coordinates of a point are given in terms of the radial distance from the origin, right, and two angles, where one angle theta is the angle of this vector with respect to the z axis, and an angle psi, which is the angle between the projection of this vector on the xy plane and the x axis, right. So, now instead of x, y, z, we are going to look at r, theta and psi, right. Why are we considering spherical equation? Because we are going to look at the mean value theorem, and the mean value theorem tells me that it tells me about the value, it tells me that how I can find the value of a function at a point by evaluating the value of the function on the surface of any sphere of any arbitrary radius surrounding the point. Since the geometry is spherical, so I am going to use a spherical coordinate system. Okay. Thank you.